Alright, this video is about the Wimshurst machine. I'm going to go over its history, its classification, what all the parts are, and a semi-watered down theory of operation, and also some troubleshooting tips for machines in this class. I apologize for all the background noise. I'm doing this in my wood shop for lack of a better space at the moment, and that means you've got other equipment running in the background. Hopefully it won't be too distracting. So this video came about as a follow-up to a document I generated. I'm going to show it and link it in the description. My version of a white paper about Wimshurst machines and everything I could find out about them. But I'm watering that down to make this more accessible, and hopefully it can be used in conjunction with that document if the viewer chooses to download it. So the history is a Wimshurst machine, which is sometimes called a Wimshurst electrostatic machine, is an electrostatic generator capable of generating high voltages. The Wimshurst machine is named after its inventor, English engineer and inventor James Wimshurst, who developed it over a few years in the early 1880s. By the way, Wimshurst is pronounced Wims, like to rhyme with hymns, and Hurst. Some people pronounced it Wimshurst, and that is incorrect. These machines belong to a class of electrostatic generators called influence machines, which separate and organize electric charges through electrostatic induction, which is also referred to as influence or electrostatic influence. And they do that instead of depending on friction for their operation. There were earlier kinds of influence machines that were invented in the preceding 2 decades, in other words in the 1860s and 1870s, but they all suffered from defects including less efficiency, unpredictable tendency to switch their polarity, and other issues, while Wimshurst's version, as described herein, has neither of those defects. Going forward, I'm just going to refer to this as the machine so I don't have to keep saying Wimshurst over and over. The machine is not always self-starting, meaning that if none of the sectors, and these are sectors here, if none of the sectors on the discs has any static electric charge when you start up the machine, then there's nothing that the machine can do to generate more, because it cannot use friction to generate the static charges. And as such, this machine will only work in reasonably dry environments. If you have a lot of humidity in the air, it either won't work at all or it won't work very well. You may still get some sparking activity, but it will be weaker than you might experience if you were in a drier climate. Right now, my home is about 50% relative humidity, so it's nowhere near dry, but the demonstration I just did shows that it still can work up to a point with this kind of environment. So don't believe that if you have a normal climate controlled space that these won't work. They just won't work optimally unless you have a drier environment. So now I'm going freehand with the camera. First off, the machine that I'm demonstrating here and using as a basis for my discussion is the one produced by United Scientific. There's their website URL. When I was evaluating which machine to buy, I saw that a number of scientific supply houses favored this machine over some of the competing models in terms of best performance and good build quality, functionality. So I went with it, and I've actually had some back and forth discussion with the tech support and product support, trying to learn more about the machine and discuss various aspects of it, and always had very good response from the people there. And the company is based in Illinois, and it's not just something that you buy on Alibaba or whatever, or AliExpress, whatever those things are called. and you never could reach anybody at the company that makes it. So I have that to say about it. So I'm going to go over and describe and identify all the parts on here, because these are pretty much common to all Wimshurst machines. The major things that you'll notice with a machine like this is that there are two discs. They are made of an insulating material, often plastic or glass, but I've seen ones with them made out of wood or fiberglass or all sorts of different things, as long as they're a good insulator for high voltages. The discs are on the same shaft, so they are concentric, and they also contra-rotate or counter-rotate. So you can see that the disc on the right is moving towards me, and the disc on the left is moving away from me. The discs are the only things that move on these machines, and they are operated typically by a hand crank. And this is achieved through pulleys. So you can see that the bottom axle there operates two large pulleys. And those are connected with belts to smaller pulleys up on the hubs of the discs. The one on the front is just a normal pulley, where the one on the rear is a crossed pulley, and that's how you get the contra rotation from a single rotation of the crank. The machines will have a base, they will have a frame, typically a front frame member, and a back or rear frame member that supports the axle that the discs ride on and the drive axle down below. And typically they will also support the bracket that holds the so-called equalizing bar. That's this metal bar here, and there's a corresponding one for the front disc. Runs down there. So those are set up that while the discs are turning, these bars are not turning. So I can show you that a little closer here. The equalizing bars do not move, even though the discs do. On the discs are sectors. There are other names for these, but sectors seems to be the most common, so I'm going with that. They are just little metal plates that are stuck on, usually with glue, to the surfaces of the discs, located outwards towards the edge of the discs. You don't usually see them down closer to the center. They are normally just made of aluminum, or just made of copper, or just made of brass, or something like that. Some machines, like this one, use alternating aluminum and copper. I think that's mostly for visual appeal, cosmetics, not for actual functionality. If there is any functional benefit from having the two different metals, I'm not aware of it. It is, however, important that there are an even number of the sectors on each disc, and both discs have to have the same number of sectors positioned in exactly the same way. In this particular machine, these sectors are made out of basically like aluminum foil and copper foil, so it's quite thin. Some machines use thin sheet metal, but that presents its own problems. I do want to reinforce what I said before, that you need to have an even number of sectors, and they also have to align crosswise, so that if you have a sector at the 9 o'clock position, for example, there will be another sector directly across at the 3 o'clock position. And if you have a sector that's at the 12 o'clock position, you will go down and find a corresponding sector 180 degrees around at the 6 o'clock position. That is necessary. So let's talk about these equalizing bars. I'm going to show the front one, but the rear one is identical. So it's a non-rotating metal bar. It has to be metal, or it could be a non-conductive material, but it would have to have a wire attached to it in order to make it conductive. And these are set up with brushes at the ends. In this particular machine, it's just some braided wire mesh that's been attached using this little spring-like gadget to the end, and you can slide this up and down the bar a little bit, or you can bend the brush around. The idea is to always make sure it's contacting the sectors as they move past without putting too much pressure on them. And so they're typically bent in the direction of rotation, like this. And you'll see the one on the other side is bent the other way, because at that point the discs are going from left to right. These equalizing bars are isolated electrically from anything else. They do not touch any other wiring, any other metallic objects. The only thing they touch is a sector at one place on the disc, and then the one that's 180 degrees opposed. That's why they're called equalizing bars, because they equalize the charge on opposing sectors as they come around. Another critical thing to know about the layout of these machines is that they always have two collectors. This C-shaped bracket here is called a collector, and on those collectors are little metallic objects called combs. The combs can take a lot of different shapes and forms. Sometimes it's a strip of metal with little points produced on it. Sometimes it's a very simple thing like this, where it's just really a piece of stranded wire where the strands have been exposed near the end, and the red part there is insulation, and then the strands are splayed out like a little fan, and they do not touch the discs or the sectors. They are separated by, it can be a little different. There's actually a disparity between the spacing here and here, but it still is enough to work. So they have many points sticking out, and they are spaced apart maybe 1/8 of an inch, maybe a little bit more, from the sectors on the discs. And what they end up doing is they remove charge from the sectors that are currently aligned with them. And I should also mention that the discs are not necessarily synchronized. While they have the same number and positioning of sectors on the discs, they're belt driven and they're not synchronized, so they could end up where the front and rear sectors are exactly in alignment, or they might end up where they're out of phase like that. It does not matter to the machine. But when a sector gets to a collector like this and lines up with the comb, then it can transfer charge. And when the one on the other disc lines up with its comb, it can transfer charge. But again, they may not be done at exactly the same time, depending on how the two discs are currently positioned. If they're lined up sector-wise, or if they're a little bit out of phase. Again, it doesn't matter to operation. Collector, two combs. Go around the other side, a collector with two combs. The job of the collectors is to remove charge from the sectors as they come by, and although the collectors on this machine are made of plastic, if you feel around the bottom, they're actually channels molded into the plastic, and those red insulated wires are tucked into those channels and end up coming over here to this metal rod here, and the collector over here goes to this metal rod here. These rods support these rods here, and these are the discharge rods. There's one on the left, there's one on the right. So the left side discharge rod is connected electrically with the left side collector, and the right side discharge rod is connected electrically with the right side collector. So when charge is removed from the sectors and picked up by the collectors, then that charge is moved to the associated discharge rods. When you have these discharge rods arranged like this, and there's electrical charges on them, they form a capacitor. So you've got two conductive objects, each with charges on them, and some space, insulating space between them, and that is the definition of a capacitor. And that capacitance can hold a charge. And that is why I said earlier that these discharge rods can hold the charge that's being taken off the sectors on the discs. Now, what are these big things here? These are Leyden jars. I'll talk about those more later on, but they are essentially additional capacitors. So you, in addition to the capacitance of the discharge rods, you also have the much larger capacitance of the Leyden jars, and that reinforces the ability of the whole machine to store up charge. Now, sometimes you don't want to have that extra capacity depending on what type of experiments you might be using the machine for. So there's usually some way to electrically remove the Leyden jars from the big picture. And that is typically done with a little switch. Could be a knife switch, could be some other kind, but it has to be able to handle a lot of voltage. And in this case, it's done with a wire jumper. This wire jumper is connected to a screw on this side, which is connected through the base to the outside metallic covering of the right side Leyden jar. And this screw terminal here goes over to the outer portion of this Leyden jar. If you remove the jumper, that takes the Leyden jars out of the picture, and they can no longer accumulate additional charge. So they are out of the picture as far as the operation of the machine goes. But normally, if you're trying to gain the most charge and get sparks or whatever other use you have for the machine, you will engage the jumper and have the Leyden jars part of the picture. Now, I said earlier that these machines are not self-starting, or may not be self-starting. If you have a environment which is not too humid, there will be natural static charges just in the atmosphere, in space, with the objects around you, and those charges move around between objects and around on objects, and some of these sectors will probably accumulate a little bit of a charge just because they're existing in the real world. Now, if you've got a very humid environment again, then that humidity tends to make it harder for these objects to accumulate charge. But if it's not too humid, some of these sectors, maybe only one, will already have some small charge on it, and that is imperative for the machine to start up. But what if you do have an environment where, for some reason, none of these sectors has a charge? You can manually get it charged up. And the usual way of doing that is the old friction method of taking a plastic rod and rubbing it with a rag or a cloth. So by friction you generate a bit of an electrical charge on the plastic rod, and then all you have to do is hold it to one or more of the sectors and let the excess electrons jump from the rod onto the sector or sectors. And then that should be enough to get the machine started. I mention that at this point in the narrative because there's a critical point to understand. The self-starting method I just described relies on friction to generate static electricity. And that's actually called the triboelectric phenomenon. I'll say that again, triboelectric phenomenon. Tribo is a Greek word meaning to rub, and even though some people will say tribo, it should be tribo. Besides charging plastic rods, balloons, cats, and other common tricks with static electricity, the triboelectric effect is actually used in lots of everyday scientific, industrial, and other things. But the whole point of this is that these machines here, the Wimshurst type machines, the influence machines, the induction machines, do not use friction to generate or manipulate electric charges. So they're in a completely different class of static electricity machinery from things that require rubbing. Alright, I'm about to start on the theory of operation section of this video, but before I do that I want to lay down a few ground rules and other bits of terminology. So, although this seems really basic and fundamental, I'm still going to go over it because there's a wide variety of viewers that might watch this video. So first off, everything is made of atoms. And for the sake of this discussion, atoms are made of positively charged protons and negatively charged electrons. Electrons are free to move around, both throughout the material that they're part of originally and also through the atmosphere, and even through places where there is nothing else, for example through a vacuum. In contrast, protons are fixed in place as part of whatever material they are part of. So electrons free to move, protons not free to move. An area of something, whether it's atmosphere or a physical object, if that area has collectively more protons than it does electrons, it's said to have a positive charge. If an area or object has more electrons than protons, it's said to have a negative charge. If an area or object has the same number of protons as it does electrons, then it has a neutral charge, neither positive or negative. Sometimes we'll say that the positive or negative state of an area's or object's charge, and we'll refer to that as its polarity. And we'll say positive polarity, minus polarity, things like that. Those are joined at the hip with positive charge and negative charge. Another concept is that like charges, meaning a negative and a negative, or a positive and a positive, they're the same kind of charge. So like charges will repel each other. This applies to individual electrons, groups of electrons, or physical objects that have electronics in them, which is pretty much everything, at least to some degree, right? The same thing can be said for protons, except that while protons might repel other protons, they're trying to repel them, but they can't actually move. But the fact that you have like charges repelling each other can still influence electrons, even if the thing that's repelling initially is a proton and can't move. Unlike charges, in other words charges that have different polarities, will attract each other, trying to move towards each other as long as they're able to do so. Again, protons might be attracted to electrons, but only the electrons can actually move, so they will move towards the protons unless something else is preventing them from doing so. So with that out of the way, this theory of operation section of the video, I'm going to keep it from being any drier than it needs to be, but there's still a number of things I have to describe, and all I'm going to do is point at this machine and talk about things. So I encourage you, if you're really interested in this stuff, to take a look at the video I'm referencing here in the video and also in the description. I use this as one of my sources for putting this video together. It's an excellent presentation using computer graphics and computer animation to help you really visualize what's happening with the charges on the machine. So, you know, after you watch this, I encourage you to watch that one if you want to see it even better in your mind. Okay, let's start out by assuming that the machine starts with one sector, and let's say it's on the front of the disc. We're not going to worry about what the other sectors are. Let's just say that this copper sector up here on top, I'll move it to be even more on top. So this sector, let's say that that one has a negative charge, just due to it existing in the real world, and things in the real world have charges. So it has a surplus of electrons compared to protons. Because like charges repel and unlike charges attract, the charge on this first sector will be able to influence the charges on other sectors if given the opportunity. And that word influence here is one reason why an alternate name to this machine, or its class of machine, is influence machines. So it'll be able to influence other things due to its charge. And this can happen when the disks rotate into a position where our first charged sector is directly across from a sector on the opposite disk. So the disks are rotating past each other, and it gets to the point where these two sectors are pretty much lined up with each other. In addition to a sector just having a charge, in other words, since I said this is a negatively charged sector, overall it has more electrons than it does protons, but that doesn't mean they're all in the same place. You'll most likely have one face of this sector more negative than the other face, which would be more positive. What'll happen here is that the sector on the back side, on the opposing disk, again assuming that this front one is overall negative, the face of the sector on the back, the one that's facing this sector, will be influenced to be positively charged, and its far face, that's the face around the back here, will necessarily become negatively charged. In addition to that, if this sector is predominantly negative, this sector will be predominantly positive. So we have taken a negative charge here and we've caused it to influence the charge on the nearest sector on the other disk, remembering that these are electrically insulated from each other. So there's not any actual movement of electrons from one sector to another. There might be a little bit, but it doesn't need to be. It's just the fact that there is a charge in the first place on this sector. It influences the charge on the opposing sector. That's an important concept here. Because these disks are contra-rotating, no sooner have those two sectors, or the rear sector, been influenced by the front sector, then they move past each other and they're sort of out of range of further influence between those two sectors. The original charge remains on this sector. Its electrons haven't gone anywhere. So as it's going around this way, now it comes into alignment with another sector on the back disk or the rear disk and influences its charge. Since this disk is turning in this direction, we end up with a whole bunch of sectors that are moving in that direction, and they're one after another being influenced by the sector on the front, our first sector as we called it. So eventually, as these disks rotate, this disk will rotate to a point where that first sector reaches the bottom end of the front side equalizing bar. So let's follow it around here. Let's say it's this one. It's going to go all the way around. Until it reaches the brush on that equalizing bar. There we go. At the opposite end of that equalizing bar, the brush up here is making contact with this sector. So now there's a direct electrical connection from that first sector up through the equalizing bar and to this sector 180 degrees across. So they're electrically connected, therefore if there's a surplus of electrons down here, which there would be for it to be negatively charged, some of those electrons will go through this equalizing bar up to this sector and give it more electrons. So now we've equalized those two to have the same amount of charge and the same kind of charge. Meanwhile, the rear disc also has its own equalizing bar, although they're positioned 90 degrees apart from each other. That one is going in that direction, this one's going in this direction. That's important to the functionality, but we don't want to go too far into the weeds on it right here. It's hard to get your head wrapped around it. But these will also equalize. So this sector down here has lost a lot of its surplus of electrons to this sector over here, which presumably could use some of them. And in the course of doing that, these two have become equalized to each other, and this one is essentially neutral now. It's probably not positive or negative, or not as much a negative as it used to be, at least. Now we get to the point where that other video I mentioned is going to be really useful to visualize what I'm talking about. I just can't illustrate it as well just pointing at things on the machine. But essentially you'll end up with, since with the normal rotation of the crank, the front disc is turning counterclockwise, you'll end up with a progression of like charged sectors coming this way, and on the rear you'll have a progression of like charged sectors going in that direction. These are going to be predominantly negative. These will be predominantly positive going in that direction. So just think about it as a progression of positively charged sectors rotating that way, and this one has a progression of negatively charged sectors rotating this way. So at any given moment, the sectors that are between the combs of a given collector will have either a positive or a negative charge on their outer surfaces, or just on the entire thing, but think about it for the moment as being on the surface. The collector on the left side, assuming that you turn the crank in a clockwise manner, this collector will see negatively charged sectors coming in this direction to it, while it'll also see there's positively charged ones going in that direction on this disc and negatively charged ones coming this way. So negatively charged sectors are coming towards this collector, and likewise positively charged sectors are coming towards this collector on the right side of the machine. So when a negatively charged sector comes into this collector, its negative charge will repel electrons from that collector comb or combs, leaving the collector with a charge that's more positive than it was before. In order for it to become more positive, the electrons that were on it have to leave, and they're leaving because they're repelled by the like charge on the sector. So you don't necessarily even have any electron movement between sector and comb on the collector. Just the charge alone being negative will repel any negative charge over here on the comb, and since these are free to move, they will move away from that comb as far as they can go, basically. And since that's connected up here to this discharge bar, that's where the negative electrons go. And likewise on the other side, when positively charged sectors comes towards it, that positive charge on the sectors will attract electrons to the collector comb rather than pushing them away from the collector comb, leaving that collector with a more negative charge than it did before. This one had a more positive charge than it did before. So far all we've been doing is moving charges around and electrons around, but we haven't actually boosted anything. So here's an important point of influence machines like this, in this particular design in particular, this Wimshurst machine. So let's look at this guy over here. We have a collector which has negatively charged sectors coming towards it. Since the combs do not actually touch the adjacent sectors, yet the two objects, meaning the comb and the sector, have opposite charges, as I just described a moment ago, this results in an electrostatic field between the sector and the adjacent comb. Because of the sharp points on the comb that I already talked about, the sharp points of all those little bits of wire, the lines of the electrostatic field are packed more closely together, so the electrostatic field at each point is stronger than it would be without the sharp points on the comb. If you just had a dull shaped object there, or just a wide piece of metal, the electrostatic field would be there, but it wouldn't be as strong as it is with those little sharp points on there. Now that strong electrostatic field attracts oppositely charged electrons from the sector or the comb, depending on their polarities, but it also attracts electrons from the surrounding air. They just, come sweeping in from the air, and they get sucked up in the influence of that electrostatic field. The same thing happens with the right side collector, its combs, and the right side discharge rod, except that the polarity is reversed, so whatever I said was positive over here is negative over here, and vice versa. The ability to use the mechanical energy of the hand crank to influence formerly randomly arranged electrons to move in an orderly and predictable and useful manner, while also harvesting free electrons from the surrounding air, which is a form of amplification. The major advantage of the Wimshurst machine is apparent. It's not just rubbing a stick with a rag. You're putting a certain amount of mechanical effort into it, and it's generating a strong electrostatic field and charge that is seemingly stronger than the sum of its parts. And this is how you can achieve large charges and high voltages with these machines. Viewed from the machine's front, with the front disc turning counterclockwise, the left side discharge rod will gain an increasingly negative charge, while the right side discharge rod will gain an increasingly positive charge. So, strong negative charge here, strong positive charge here. Because opposite charges attract, these two charges between here and here will want to equalize by movement of the excess electrons on the negative side towards the electron poor positive side. When the charge between the discharge rod ball ends is high enough, we can say that a large voltage is now between these two balls. With the increasing voltage, the air between the balls becomes ionized, which is to say that the atoms in the air between the balls are induced to lose electrons by the strong electrostatic charge. So the space here in the air now has an excess of free electrons. This helps the high voltage to start pushing electrons across the so-called spark gap, and of course that is a spark occurring at that point. Once the electrons start to go across, as long as there's still charge accumulated between these two, the air becomes more ionized by the initial spark, and then that makes it easier for the remaining charge to equalize by pushing a lot of electrons across. When the spark extinguishes, there's probably still a little bit of charge left, but you can say that the two discharge rods have pretty much equalized their charge once a spark has occurred and gone away. If you turn the crank quicker and spin the discs quicker, you move the charges around more quickly, you accumulate new charge more quickly, and therefore the voltage will develop enough to make another spark happen sooner than it would be if you were cranking more slowly. Remember that the spherical balls here are without any sharp points or abrupt edges, and that discourages those electrons that have accumulated over here, this charge that's been built up It discourages them from trying to move across, leaving a well-defined point. When you have electrons and there's a charge and it's trying to move the electrons out, it moves easier from a fine point than it does from a broad surface. That's one reason why things like lightning rods are sharp points instead of just some big metal plate or something. The charge leaves more readily from a sharp point or abrupt edge. To avoid premature sparking and equalizing, you want a surface that's as devoid of sharp or abrupt points as possible, and that's why they're shaped like balls. If you were just storing charge in the capacitor that these two discharge rods comprise, you would get sparks, but they would be a little bit on the weak side, because once the spark occurs, it equalizes very quickly and there just isn't that much mass of electrons trying to get across, so it extinguishes very quickly. If you add the Leyden jars in here with their much greater charge, then there's more oomph, if you will. The voltage might actually be the same, but once the spark starts, there's more electrons that are jumping from one ship to the other, and the spark will last longer and be fatter and just more impressive if you're interested just in the spark. But Wimshurst machines can actually be used for actual scientific things and operating certain kinds of equipment that need high voltages. And sometimes you don't want all that extra capacity. So that's why these are almost always equipped with some way to defeat the Leyden jars without actually removing the Leyden jars from the machine. I'd said earlier that I was going to talk about the Leyden jars in more detail at a later point, and that point has now arrived. So Leyden jars were developed in the year 1745, actually by two European scientists who were working separately from each other without knowledge of each other's work, so independently invented in the same year by two different people. One of them was a German named Ewald Georg von Kleist, or Ewald Georg von Kleist, and he called his invention the Kleistian jar, so he named it after himself essentially. The other inventor was a Dutch fellow, Pieter van Muschenbroek, if I'm not mispronouncing that, in the town of Leiden, Netherlands. That's spelled L-E-I-D-E-N, and he called his invention the Leyden jar, so he named it after his town. The town name was also spelled Leiden, L-E-Y-D-E-N, but has the same pronunciation regardless of the spelling, and over the years these jars have become to be named Leyden jars with the L-E-Y spelling. Leyden jars are just a form of capacitor, usually with an open-ended jar or tube. The original ones were formed with glass jars, not that dissimilar from a bottle of water or a jar that people who can fruits and vegetables would use. But it could also be just a tube of glass or plastic or something like that. The inner surface of the bottle or jar or tube is lined with a thin metal film like aluminum foil, and the outer surface of the same object is lined with another layer of foil. The insulator, that's what the jar or the tube is there for, and the two metal plates, the inner and the outer foils in other words, form a capacitor. That's the essence of a capacitor. Typically, to get at the inner foil, a metal rod is run down the inside of the tube or in through the neck of the jar, and then some wire of some kind is connected from that rod to the metal foil on the inside. And the outside you can just contact by putting something up against it. So a typical Leyden jar gets the outer plate connected by various means, and the inner plate is pretty much invariably accessed through a rod coming out the top. There's a rod here, but it's hidden inside this plastic housing. And as said before, if this jumper is not made, then there is no connection from the outer plate of this Leyden jar to the outer plate of this Leyden jar, and that makes an open circuit, and it's, even though there's capacity here and here, they're not connected to anything at their other end, so they don't really accumulate any charge, and they can't let any of their charge out. They're just there without doing anything. But if you connect them together like this, now you have this negatively charged area going down the rod in this Leyden jar, the outer plate going through this jumper to the outer plate of this one, another charge is built up in here, and its other side is the discharge rod over here on the right side. So between here and here you have one big capacitor, or technically two capacitors in series. There isn't actually any requirement to have two Leyden jars on a Wimshurst machine. Other than that, having two gives the machine a nice symmetrical appearance, and for the simple convenience in connecting the jar's central rods to the nearby discharge rods. They're just right there, so you might as well have two jars. It just makes everything easier. There is a downside to having two jars, though. These are, again, capacitors, and if you know much about capacitors, you'll know that if you put two capacitors in parallel, they act like a capacitor with twice the capacity, or capacitance. But if you put two capacitors in series, collectively they act like one big capacitor with half the capacity of just one of them. You'll often put two capacitors in series when you need to handle higher voltages, however, because only half of the voltage will be across each Leyden jar. So if you think about one battery, for example, there's maybe 1.5 volts from end to end. But if you put two of them in series, you'll get 3 volts, but if you measure across either one of them, you'll only get 1.5 volts. Same thing here. A machine like this can generate between 30 and 70,000 volts, or 30 kilovolts to 70 kilovolts. And that's a lot for a capacitor to withstand. Normal capacitors like you'd buy for electronics are in no way able to handle such high voltages. That's where Leyden jars come in. Even though they're very old technology, their construction means that they can withstand a lot of voltage. And when you put two of them in series, they can handle twice the voltage overall, but each one is only seeing half of that. But by putting them in series, you're cutting their capacity in half, so their ability to store electrical charge is half of what it would be with just one. But you can't do anything about that here by removing this jumper. This is just here to allow you to take the Leyden jars out of the picture. It is not there to have you just operate one Leyden jar. And this machine isn't really set up conveniently to do so, although if you remove this and then hooked up some test leads with alligator clips and things, you could probably make it work with just one of the Leyden jars being functional. I haven't tried that. I'm not suggesting anybody do that. Assuming that the machine is configured to produce a negative charge at its left collector and discharge rod, and a positive charge at its right collector and right discharge rod, the inner foil of the left Leyden jar will be negative, and the inner foil of the right Leyden jar will be positive. Because opposite plates of capacitors will have opposite charges, that means the outer foil of this jar will be positive, and the outer foil of this jar will be negative. With the outer foils of the two jars connected together, the polarity of the two series connected jars will be minus to plus, just like when you put two batteries in series, you connect the plus of one to the minus of the other one. So it's not like both of these will be negative. So we go from a negative collector and discharge rod. The center is negative. That means the outside must be positive. And because it's connected in series, this one will be negative on its outside, which means the center part will be positive, and that's what we know the collector and discharge rod here are, so it all adds up. A few words about electrical safety. Typical high voltage machines such as Van de Graaff generators and Wimshurst machines and other things like this can deliver pretty high voltages, but voltage by itself isn't all that dangerous. What's really dangerous to people, at least living organisms, is the amount of current that moves through your body when you get an electrical shock or you're put in a position of having current flow through you. The higher the voltage, the greater the likelihood of it pushing more current through your body or through your hand or between two fingers or whatever. And a good rule of thumb for small Wimshurst machines like this is that they probably can't deliver much more than, say, 30 microamps of current, which isn't enough to hurt you. I mean, it's enough to startle you and make you jump back and maybe make you say ouch real loudly or some other choice words, but it probably would not kill you unless you're standing on a ladder or something and it makes you fall over and you hit your head, you know. Lots of things can happen. And you can't predict exactly what the current will be under a given situation. So when using a machine like this, it's always best to stand back from the machine. You know, don't let kids and your cat walk right past it when you're operating. You know, keep a bit of a distance. The charges will equalize just through the atmosphere, but when you're done with the machine, it's a good practice to use the handles on the discharge rods to move them together and leave them that way. As I said earlier in the video, these machines work better in a drier atmosphere than in a more humid atmosphere. So the amount of spark you can get on these depends a lot on the environment, as well as how fast you crank the crank and how the machine is adjusted with its comb spacing and how well the brushes are making contact. A number of different things can influence it, whether or not you're using the jumper that engages the Leyden jars. If you find that the balls are too far apart to allow the available voltage to push the charge across the gap, in other words, to create a spark, the charge is still being accumulated, and at some point something else is going to break down. You can get small sparks jumping between other points on the machine besides up here. You can get sparks jumping from one sector to another. You can get ones jumping, you know, from the equalizing rod to the outside of a Leyden jar and things like that. If you're cranking the machine and you don't see any sparks up here, but you're hearing the little snaps and crackles of sparks, that's where you've reached the limit of the machine for your current environment. In a more humid environment, the sparks will be more likely to jump in places you don't want them. In a dry environment, it'll probably be better. But if you're seeing or hearing those sparks and it's not happening up here, your only real recourse is to, you know, move the ball ends a little closer together until you start doing the equalization here instead of some other part of the machine. Okay, I'm going to close this video with some general troubleshooting tips. If the machine does not seem to be producing sparks at the place where they're supposed to be between the ball ends of the discharge rods, here are some things you should check. First, is the humidity of the surrounding air more than a moderate level? And I'm not putting any exact number on that. Low humidity is the best for best performance. If it's really humid, the machine might not work at all, or it might just give you very weak sparks with the ball ends really close together. If you have the option to turn off your humidifier for a day, let's say it's in the winter and you're in the north, the air will get pretty dry pretty quickly, and that might be a way to get the machine to perform a little better, at least for a demonstration or something. If you're not getting a spark, check to make sure that both discs are turning smoothly and at about the same speed. They must be for this to work. If only one disc is turning, or if for some reason the belts are messed up and they're turning the same direction, maybe something got jammed in between them and it's forcing them to not move properly, that will be a deal breaker right there. If they're not moving properly, the machine just will not work. Are the brushes on both ends of the equalizing bar making good contact with the sectors? Make sure that they all are. There's 4 places where brushes touch sectors, and you have to inspect them all. And are they contacting both of the opposite 180 degree separated sectors? Sometimes you might end up with these misadjusted and it's touching this sector, but it's missing this sector. It might be just a little off to one side or the other. If even just one of those is messed up like that, the whole machine will stop working. So you need to have that all sorted out. Try to adjust it so they're not putting too much pressure on here. These are just foil and they'll wear through if you have too much brush pressure. They'll probably still wear through eventually if you use this a lot. This is really for demonstrations. You know, you wouldn't want to use this particular machine continuously because it will eventually wear through the sector foil. A light contact pressure is best as long as it's actually making contact. If you're not getting a spark, check, is the machine dusty? Or is there any condensed moisture on it? Maybe it went from a cooler room to a warmer room and you've got a tiny amount of condensation on it because of that. That will prevent it from working until you can arrange to have the dust or moisture removed. It's best to store these with a cover over them because there's just a lot of places on here for dust to be attracted to and accumulate and be awkward to clean off. Is the jumper between the 2 Leyden jars made properly? If it seems to be and the machine's not working, try operating it without the Leyden jars and see if that helps. Because if you have a short circuit in one of your Leyden jars and they're coupled together, putting them into the picture, electrically speaking, that short could prevent the machine from working. So that's a bit of troubleshooting with the Leyden jars. Did you happen to forget and leave the discharge balls touching? That'll keep you from getting a spark. Are the combs adjusted to have the proper amount of space between themselves and the discs or the sectors? Are the ends of the points splayed apart instead of just being all jammed together? Those are things to check. Finally, have you paid your correct tribute to Zeus or Jupiter or Jove recently? If you haven't kept the appropriate gods happy, who knows what'll happen with this magic electrical stuff.